Welcome, my name is Riccardo Caivano and I'm going to present our research about defect-driven topology optimization, in particular the extension of the TopFat algorithm to the commercially available software HyperWorks and its validation by means of a complete benchmarking with the original results. Before starting, I would like to introduce my colleagues, Dr. Andrea Tridello and Professor Davide Paolino from Politecnico di Torino, and Professor Filippo Berto from Norwegian University of Science and Technology. The presentation will be divided in 5 main sections. In the first, I will introduce the topology optimization framework. In the second, I will briefly explain the key factors affecting the fatigue response of additive manufacturing products. In the third section, I will introduce the TopFat algorithm aimed at including the defect population analysis within the topology optimization setup. In the fourth section, I will detail how to extend the TopFat procedure to the commercially available software HyperWorks and its benchmarking validation. And lastly, conclusions and final remarks.
Topology optimization can be defined in several ways. Here, I reported a very intuitive and practical explanation. Topology optimization is the procedure aimed at finding the best material distribution within a certain loaded domain, chasing an objective, and under prescribed constraints. As for the material distribution, one of the most employed methods is the so-called density-based method. In this method, the domain is discretized in finite elements, and each element has its own relative density, called ρ. The relative density is 0 if the element can be considered as void material, whereas it is 1 if the element can be considered as full material. In the end of the optimization, the ρ equal to 1 zones will define the final topology. As for the objectives, they can vary a lot. The most common are the mass minimization and the stiffness maximization. Likewise, the constraints can be both geometrical, such as overhanging limitation, or structural, such as a maximum von Mises stress. For example, looking at the image, the classical simple supported beam is optimized for stiffness maximization under a volume constraint. The topology optimization can find the optimal structure, even the global optimal structure, if the optimization process is well posed. Anyway, the final topology is optimal only under the prescribed constraints imposed at the beginning of the optimization. Just to have a visual example, let's look at the L-shaped beams he reported. In both the cases, the L-shaped domain is located in the upper edge and loaded in the right upper corner. The stiffness has to be maximized under a volume constraint, a very classical topology optimization setup. Looking at the left topology, no stress constraint has been imposed, and therefore the re-entrant corner is fully included in the final topology. The reason is that this maximizes the stiffness of the final structure, but in that point, in the re-entrant corner, high stress peaks can appear, and there is no control on them. On the contrary, the final topology on the right has been achieved including a von Mises stress limit. In this case, the topology is less stiff, but is structurally safe, and, as a consequence, the topology optimization can be employed to safely design components. Topology optimization has been studied since 1980. However, the final geometries obtained with this method were almost always complex and very difficult to be realized through traditional and conventional manufacturing techniques. Recently, the advances of additive manufacturing processes allow us to produce those geometries, even if convoluted and intricate. However, as discussed before, it is crucial to understand which are the key constraints to be included in the topology optimization setup, in order to safely design parts for the additive production. Looking at the life of the components, if the quasi-static regime is considered, a constraint on the von Mises stress may be sufficient. Instead, if the fatigue regime is considered, several questions must be answered to understand which constraints and fatigue model must be included. So, for example, how AN parts respond in the fatigue regime, or what drives the fatigue response? The most important aspect to consider is the defect population, which affects the AN product's fatigue response. Indeed, AN parts are characterized by a non-negligible presence of process-induced defects, such as pores, cluster of pores, and lack of fusion. These defects cannot be eliminated, even if a perfect process parameter setup is employed. In this condition, classical fatigue theories may not be sufficient to predict the fatigue limit of the component. In particular, they may overestimate the real fatigue response of the part. The most suitable theory in this sense it is that of Murakami. His model can predict the maximum first principle stress which can let nucleate and propagate a crack from the most critical defect. If that first principle stress threshold is not exceeded, then the part can be considered safe, even in presence of defects. With the aim of evaluating this limit, the defect population must be known. However, it can be accessed only after the part production, with, for example, non-destructive techniques, when the design phase is already concluded. In order to access this defect population during the design phase, it has to be estimated statistically a priori. Murakami demonstrated that the defect populations follows the largest extreme value distribution, Levd. Equation 1 expresses the Levd distribution. It states the probability P of finding a defect with dimensions square root of A, which represents an equivalent measure for the defect's area. As it can be seen, it is characterized by two main parameters, mu and sigma, which are the location and scale parameters of the distribution respectively. These parameters can be estimated experimentally looking at the defect population of several samples. Reversing equation 1, it is possible to foresee the largest defect area, square root of A, under a certain probability P, and this can be employed within equation 2. This equation expresses the link between the defect population, the stress ratio, the material parameters, and the maximum allowable alternate first principle stress, sigma f. This limit is the threshold which must not be exceeded in order to have a safe part in presence of defects. This limit over the first principle alternate stress can be included within the topology optimization formulation. In particular, here it is detailed the formulation of the TopFat procedure. The formula can be quite easily understood looking at the different terms that compose it. Basically, the aim is to find the relative density of each element in the domain, that is the topology, which minimizes the global complements. Meanwhile, the equilibrium must be effective, and this is guaranteed by the finite element model. The final value must be a fraction of the initial one. The von Mises stress must not exceed the threshold sigma s, in other words, the quasi-static limit. The first principle alternate stress must not exceed the threshold sigma f, only where traction load is applied, that is, the defect-driven fatigue limit by the previous equations. Lastly, the relative density must belong to the range 0, which means void material, and 1, full material. The TopFat procedure has been solved in MATLAB, and actually it is a property code. However, even if this algorithm is well working, its applicability on industrial cases is limited. The possibility to extend the TopFat procedure to commercial software would let industries and academics include the defect-driven constraint within the topology optimization to safely design AM parts. This extension brings many positive aspects, such as complex 3D meshes, assembly evaluation, straightforward post-processing, and much more, without any coding procedures. The only required modification with respect to the previous topology optimization setup is that HyperWorks does not admit a constraint of the first principle alternate stress, whereas on the first principle maximum stress. For this reason, the Murakami limit is transformed into a limit of the first principle maximum stress, according to the highlighted equation.
Let's consider the geometries used in the original paper. They are the L-shape, the cantilever, and the corvette structure, respectively. They are supposed to be manufactured using a common steel alloy by AM process. The volume fraction for the final topology is set to 30%, and the yield stress is 580, 620, and 660 megapascal, respectively. The applied load and the number of elements will be detailed later for each case. In the table, all the data related to the defect population and the material info are reported. They lead to a common fatigue limit on the first maximum principal stress of about 510 megapascal. As for the L-shaped beam, the result obtained using TopFat is reported on the left, whereas the result obtained using HyperWorks is reported on the right. The force in this case has an intensity of 800 Newton, and it is applied downward on the right upper corner. 6,400 second-order elements have been used. The TopFat solution is faster in reaching the convergence, but the two topologies are quite different, especially in the lower left portion of the domain. The HyperWorks solution is 7% stiffer, and the stresses are far below the limits. However, the re-entrant corner is partially included in the HyperWorks final topology. The differences are reasonable since two different solvers, element types, and stress evaluations are employed. Anyway, the results are feasible with respect to their initial constraints. As for the cantilever beam, again, the result obtained using TopFat is reported on the left, whereas the result obtained using HyperWorks is reported on the right. The force in this case has an intensity of 1000 newtons, and it is applied downward in the center of the right edge. 20,000 second-order elements have been used. The TopFat solution in this case is slower in reaching the convergence, and two topologies are remarkably different, but both feasible. The HyperWorks solution is 10% stiffer, and the stresses are far below the limits. However, as for the L-shaped beam, the most stressed zones are partially included in the HyperWorks final topology, whereas they are not in the original TopFat one. The so different results can be justified with the same reasons expressed for the L-shaped beam. Lastly, as for the corvette beam, the result obtained using TopFat is reported on the left, whereas the result obtained using HyperWorks is reported on the right. The force in this case has an intensity of 3,500 newtons, and it is applied downward on the right upper corner. 17,700 second-order elements have been used. The HyperWorks solution is not able to reach the convergence, and messy web truss-like structure appear. Furthermore, the HyperWorks solution does not present a feasible design, and both the stress constraints are not respected. The extreme geometries of the corvette structure causes the HyperWorks solvers to fail. Instead, the original TopFat algorithm is designed to work properly even in these hard conditions. Overall, the HyperWorks software can unlock wide-ranging applications, even in 3D. However, it may struggle with geometrical singularities. In order to exploit the HyperWorks potentialities, it may be sufficient to round these geometric singularities, operation which does not imply any particular complex work. To conclude, topology optimization is a powerful tool for lighting structures and maximizing component performance, with possible outstanding positive effects on aviation, aerospace, racing, and many other industrial sectors. However, if the physical limits of the material are not included in the algorithm, the final component may fail under the imposed loads. Additive manufacturing techniques are suitable for producing topologically optimized parts. However, they suffer from process-induced defect presence. It is crucial to understand that these defects drive and lower the fatigue response of the part, and they must be included in the topology optimization setup. These can be done including the defect presence according to the Murakami model as a constraint on the first principle maximum stress, as done in TopFat. The commercially available software HyperWorks is able to effectively exploit the TopFat method and extend it to many other rare cases, except for extreme geometrical conditions. The present case study guarantees the extendability of the TopFat procedure to a commercially available software, unlocking the possibility to safely optimize components under defect-driven constraints without the need of dedicated code. Thank you very much for your attention.